Hello class, this is CSE-4600, Section 1, Week 4, Spring 2025. Okay, so let's recap our discussion on what we were talking about regarding interprocess communication and race conditions. So this is a recap of what we covered in last class. So as far as processes are concerned, they think they have the entire computer to themselves, even though there's only one computer's worth of resources to go around. That said, it's quite common for processes to need to talk to other processes. This is called interprocess communication. There are issues that we need to resolve regarding interprocess communication, or IPC, how to pass information between processes, making sure processes don't get in each other's way, and making sure operations are done in the correct order. All of this also applies to threads, except for the first point, because if we have threads that belong to the same process, then it's trivial for them to share information with one another because they're all sharing the same memory space. So what we're going to talk about here will apply to both processes and threads, but yeah, that's something to keep in mind. So the main issue that can come up with interprocess communication is an issue called a race condition, called so because processes are racing one another. Let's consider a simple example of process A wants to write something into a spooler directory. This is a directory where files go to be printed. Process A must follow a sequence of steps. First, check where the next available slot is, write a file into that slot, and then increment the value of in, that's the value for the next available slot. Increment that so it points to the next available slot. So process A performs step 1. Find out what the next available spot in the spooler directory is. So that's slot number 7. Let's say at this point, process A is interrupted so that process B runs next. Process B performs those next 3 steps. So process B performs the same 3 steps that process A was trying to do. Check what the next available slot is, write a file into that slot, and then increment the value of the next available slot so that instead of 7 in this case, it becomes 8. So now, the next available slot is 8. Process A eventually runs again, so it had already performed step 1. So process A already has the information of the next available slot, and that is slot number 7. So it writes a file into slot number 7, and then increments in to be the next available slot, which is slot 8. So here's what happened. Process A still thought that the next available slot was slot 8. No, the next available slot was slot number 7, because process B had interrupted process A's writing into the slot. Process A still thought that the next available slot was number 7, even though it was number 8. It had already performed step 1 of find out what the next available slot was, which was slot number 7. So when process A wrote into slot number 7, it overwrote process B's file, so process B's file never gets printed out, and process A's file gets printed out instead. That is a race condition, and to debug these is not fun. They're also called race hazards, by the way. Most of the time, your code will work as expected, but sometimes you'll get something absolutely weird. You might get stuff being printed out in the wrong order, or you might have, say, a summation of terms, and the result is not what you expect. Or worse, every time you run it, you'll get different results every time. This is the problem of a race condition, and the reason why we're talking about this is because, well, we have high core count CPUs now, like 8, 12, 16, 20, and more cores. So, core counts like this is not uncommon anymore. So now we need to know how to not only write code to leverage these multiple CPU cores, but also in a way that ensures that the steps of execution aren't jumbled up and we get so we don't get incorrect results. There's a song where someone was trying to be fly for a white guy. He gets a edgy number 13 tattoo, but the tattoo parlor screwed it up and they drew 31 instead. I'd like to think that that was because of a race condition. They were doing one digit at a time, but they did it in the wrong order. So the key to avoiding race conditions is simple. We need to recognize that there is sections of code that can only be accessed by one process at a time. That section of code is called a critical section. The textbook calls that a critical region, but I'm calling it a critical section. The key thing is to make it so that only one process can enter the critical section at a time. So, with the spooling example, just writing stuff into the spooler directory, the code where you write stuff into the spooler directory, that is a critical section already. So really what we need to do is this. If process A is already writing stuff into the spooler directory, process B should wait its turn. And that is the flow, and that's the flow of work if we recognize that trying to write into the spooler directory is a critical section. So process A enters its critical section. Process B tries to enter the critical section, but it's blocked because process A was already there first. So process B is blocked. It waits its turn for process A to leave, and then B can enter its critical section. On a single core, on a single processor system, the simplest solution is to have each process disable all interrupts right after. On a single core system, the thing that happened with process A in our spooler directory example was it got interrupted by the CPU scheduler, signifying this next process needs to run next. So, if we want to make it so that process A runs uninterrupted, it would silence its phone so it can't hear the ringtone, so it'll do its work without interruption. That mechanism is disabling interrupts. So the simplest solution is to disable interrupts before you enter a critical section, but remember to turn them on right after you leave. That way processes can read and update shared information without any other processes intervening. The problem with this is you're giving programmers the ability to turn off interrupts, which is a power that is too disastrous if it goes wrong. The danger is forgetting to turn back interrupts on. There's also more. If we have a multi-core CPU, disabling interrupts only affects the CPU that executed the disable interruption. On the other hand, it's frequently convenient for the kernel to disable interrupts for a few instructions while doing some other operations. The point is this. Although we can disable interrupts, it's not an appropriate solution for enforcing mutual exclusion. Because once again, what if you forget to turn it back on? Interrupts are used by the operating system to signal that certain things have happened. Kind of like the doorbell on your, it's like a doorbell on your door. That is an interrupt to signal, hey, there's someone at the door. We could have other types of interrupts, such as the fire alarm saying, hey, there's a fire, or more commonly, a false alarm. But you wouldn't get to know that until after you've evacuated. My point is, if we disable these interrupts, something important might happen, and we won't have a means of responding to it. Another solution is what's called a spin lock, where we have code written in C. It can also be C++, but let's assume it's C code and assume we only have two processes. This is called a busy wait. We have two processes and one shared variable called turn. The turn variable indicates whose turn it is to go next. So let's set this turn value to initially be 0. That means process 0 gets to go next. Process 0 runs these 4 lines of code. The first one is actually an infinite loop, while turn does not equal 0, and then semicolon. That is an infinite loop, where process 0 checks this condition, turn does not equal 0. If that expression evaluates to false, process 0 immediately breaks out of the loop. If that expression evaluates to be true, it's going to check the expression again, and again, and again, and again. It will only break out when some other process changes that turn value from... Process 0 will only break out if some other process changes that value to 0. Only then will process 0 break out. Okay, but let's assume that turn was already 0. Process 0 checks that expression. It evaluates the expression, turn does not equal 0. Does 0 not equal 0? No. So it breaks out of the loop. Then, now, process 0 can enter its critical section. Okay, so let's say at the same time, process 1 wants to enter the critical section next. While turn does not equal 1. Does 0 not equal 1? Yes. That means it's process 0's turn to go next. So process 1 must wait. It checks it evaluates the expression turn does not equal 1 again and again and again. It's gonna break out. It will only break out of the loop once that turn variable changes to 1. When process 0 is done with the critical section, it will change the value of turn from 0 to 1. And then it enters some non-critical section of the code. Meanwhile, while process 1 was repeatedly checking this condition again and again and again, the turn variable changed from 0 to 1, and suddenly 1 does not equal 1 evaluates to false. Process 1 breaks out of the loop, and now it's allowed to enter its critical section. After that, it changes the turn to 0, and now that indicates it's now process 0's turn again. This is called a busy wait, and it's scalable to any number of processes. When we scale it up, we should replace that turn equals 1 and turn equals 0 into turn equals turn plus 1 in parentheses modulus the number of processes. That way, if you have, say, 3 processes, one process will increment it from 0 to 1, the next process will increment from 1 to 2, and the next process would increment it from 2 to 3, but because of the module operation, it'll roll back to 0. So now we have a mechanism to make sure that only one process at a time can enter the critical sections. And this works, and so does another solution called Peterson's solution. The problem with these solutions, including the one that uses a TSL in CPU instruction, is that they all use what's called a busy wait. When we check that condition, turn does not equal 0, or turn does not equal process ID, the CPU is evaluating the same expression over and over and over again for each clock cycle. Although this will make it look like the process is doing work, it's doing unproductive work. So I'm gonna have to make your video for your next lab tomorrow, so it's gonna be a little bit delayed. But when I do make that, I might have to demo some other code to show you what it's like to try a busy wait. So that's the problem with using Peterson's solution and a busy wait. When a process enters its critical section, when a process tries to enter its critical section and it can't, that process performs an infinite loop until it can. This is a waste of CPU cycles. To prevent that, the idea is this. Why don't we just make processes that are waiting go to sleep, and then we wake them up once another process leaves its critical section? There's also another problem that can happen called the priority inversion problem. A high priority process runs when it's ready to run. It takes precedence over a low priority process. At some point, the low priority process is in its critical section when the high priority process is ready to run. This makes the high priority process begin busy waiting. But since the low priority process is never scheduled while the high priority process is running, the low priority process is actually stuck in its critical section while the high priority one waits forever. This is called priority inversion, and that is its own problem. We're not going to talk about priority levels just yet, not until we get to CPU scheduling. We're assuming that processes are all equal in the sense that when it's their turn to run, they run for about the same amount of time as any other process. So if all processes get to run for like 10 milliseconds at a time. It's not unreasonable to have different priority levels, but we'll get to that when we get to CPU scheduling. Let's consider one problem, and that is the producer's consumer's problem. It's also called the bounded buffer problem. There are two types of processes. Producers, which puts data into a shared buffer, and consumers, which takes data out of a shared buffer. We can also generalize this to any number of producers and consumers, but let's just go easy and start with one of each. Trouble arises when a producer tries to add something to an already full buffer. Likewise, trouble also happens when a consumer tries to take from an already empty buffer. The solution to either case is to have the process go to sleep. So when a producer tries to add to an already full buffer, it goes to sleep. When the consumer takes stuff out of the buffer, it wakes up the producer so that the producer can start adding stuff to the buffer. Likewise, if the consumer tries to take from an already empty buffer, it goes to sleep. So when the producer adds stuff to the buffer, it wakes up the consumer, telling it, hey, there's stuff you can take out now. So they wake up each other. There's a way where that can go wrong, but for this to work, we need to add another variable, count. Let's say this is a buffer that can hold 100 items. So 1, 2, 3, the producer adds stuff to the buffer, 4, 5, eventually it gets to the 100th item, and then when it tries to add the 101st item, before the producer adds anything, it checks the count to determine whether it's full already. When it tries to add the 101st item, before it does that, it checks the count to see if it's at its max, which is 100 in this example. When it realizes it's at its max, the producer goes to sleep. Likewise, 99, 98, 97. The producer takes stuff out of the buffer. Before it does that, it checks the count to make sure it isn't 0. If it is 0, the consumer will go to sleep. So here's some code that illustrates what a solution to the producer's consumer's problem would look like. However, there's actually a problem here. There are no sleep and awake routines in the standard C library. Such routines would be provided by the system itself. This code actually has a race condition because access to count is unconstrained. Let's see how that would pan out. Remember, before the consumer takes anything from the buffer, it checks to see whether it was 0. Before the producer adds anything to the buffer, it checks whether it was already full. In this case, it's 100. So let's say the buffer was already empty, and the consumer has just read count to see whether it was 0. The CPU scheduler decides it's now the producer's turn to start running. So the consumer was already running. The CPU scheduler decides it's now the producer's turn to run. So the producer is now blocked. It's not running right now. The producer adds an item to this empty buffer, increments count, and then sends a wake-up signal to the consumer. But the consumer was not sleeping. It wasn't sleeping. It was blocked. So that wake-up signal actually gets lost. When the consumer runs again, it will test the value of count. It'll take something out of the buffer, and it'll go down to 0. When it sees the value is 0, it will go to sleep. Eventually, the producer will start running, and it will fill up the buffer completely because the consumer was already asleep, and then the consumer and the producer will then be asleep, and they can't wake up each other, and now we're stuck. We get deadlock. And the problem here is we sent a wake-up signal to what we thought was a sleeping process, except it wasn't asleep. Is there a way we can get this, we can save wake-up signals? Well, there is a way to do that, but one way is to add a wake-up waiting bit. When a wake-up signal is set to a process that's still awake, that bit is set. If a process were to go to sleep while the bit was set to 1, the process will stay awake and set the bit to 0. This way we don't lose wake-up signals, and this bit is cleared by the consumer with every loop iteration. So that is one way we can solve the issue, but a much better solution is much more robust. It's a means of saving wake-up signals. So once again, what went wrong is when the consumer was blocked from running so that the producer can run. The producer added stuff to an empty buffer and signaled to the consumer to wake up, but it wasn't asleep, it was blocked. Eventually, the consumer takes stuff from the buffer and goes to sleep. Eventually, after that, the producer adds stuff to the buffer and goes to sleep. And now suddenly, both processes are asleep and they can't wake each other up. That is the problem. In 1965, Edgar Dijkstra suggested an integer value to count the number of wake-up signals that were saved. This came about a new data type that we now call a semaphore. This is an integer value that indicates how many wake-up signals were saved. Dijkstra also proposed two operations on semaphores. They are generalizations of sleep and awake, and we call them up and down. The down operation checks to see if the value is greater than 0. If so, it decrements the value and continues. If it is 0, then the process goes to sleep without completing the down operation. The up operation increments the value of the semaphore. If a process was sleeping on that semaphore, unable to complete that down operation, it's awoken and it's allowed to complete the down operation. In the case that there are multiple processes, let's just say one is chosen at random. The important thing about either operation, about up and down, is that they are atomic operations. We cannot cut them up into smaller operations. They cannot be interrupted by anything else. Atomic in the sense of uncuttable. Like how, like, you can, it's this idea in physics and like chemistry where you can keep cutting up a substance until you get to some fundamental unit. If you did that with gold, at some point you would get down to a gold atom. You could do this for a uranium atom, and you could keep cutting gold and uranium atoms even further, but at that point they stop being at gold and uranium atoms, especially if it's a uranium atom. If you split a uranium atom, the constituent parts are no longer uranium atoms. There's something else. Insert Oppenheimer reference here. So, the operations are up and down. These are generalizations of sleep. The operations are down and up. They are generalizations of sleep and awake. Sometimes you'll see V and P, and they come from the Dutch words for raise and try. I'm not going to try to pronounce these, but they mean raise and try VNP. So the code for this producer's consumer's problem might look like this. So the producer performs the following sequence of steps. It produces an item. It performs down on a semaphore called empty, but also performs down on a mutex. So I actually need two things here. The first one is a mutex, and the other one is that special variable for the count. So, produce an item, decrement the empty count, and then enter the critical section. If at any point we fail to do one of those down operations, that means some other process was already in the critical section. We'll complete that when that other process performs its up operations. But let's just proceed anyway. We call down and pass in empty. We call down and pass in our mutex. And then we add an item to the buffer. We call up and pass in the mutex, and then we call up and pass in full. So yeah, we actually need 3 semaphores for this. One for something called a mutex, another one for something called empty, and another one for a variable called full. The consumer, meanwhile, calls down on full, calls down on mutex, removes an item, calls up on mutex, calls up on empty, and then consumes an item. So we need, as I said, we need 3 semaphores. One is for full to indicate the number of buffer slots that are full. One is for empty to indicate the number of buffer slots that are empty. And the third one is a mutex. A mutex is a special case of a semaphore. It's called a binary semaphore because it can only be of one of 2 states, 0 or 1. We use that special semaphore to enforce mutual exclusion. Think about it like this. If a resource can only be accessed by one process at a time, and it's available, we say there's 1 of them. Once it's in use, we say there's 0 of them. Once that resource is no longer in use, now there's 1 of them available again. So yeah, the thing is, we can also use semaphores to count how many resources are available. Have you ever looked at the parking lots at CSUSB and noticed those signs that say there are like 300 parking spaces available? That's actually a real-life example of a semaphore. That's counting how many available parking spaces there are. When a car parks at a parking space, that count goes down. So now there's 299 spaces left. When a car leaves, that count goes up. There are now 300 parking spaces left. Let's say there's only 1 parking space left. A car goes in, the count goes down, and now there are no more parking spaces available. Another car leaves, another parking space becomes available, that count becomes 1. Some parking garages they go all out and put indicator lights on the ceiling indicating which parking spaces are available. That's a real-life example of a semaphore, by the way. And now you know. The thing about semaphores and the up and down operations is this. As long as each process calls down before entering a critical section, followed by up after leaving its critical section, we can guarantee mutual exclusion. We can also use semaphores for synchronization, making sure that certain events happen in a specific order. If a semaphore's ability to count is not needed, and it's indicated and it's used to indicate one of 2 states, locked and unlocked, or available and not available, we can use a mutex instead. In theory, we can just use a single bit for this, but in practice, it's just an integer that's either 0 or 1. A mutex has 2 procedures that are used alongside it. One is mutex lock. When a process needs to access a critical section, it calls mutex lock. If it's unlocked, then the process is free to enter the critical section. If it is locked, then the process is blocked until another process calls mutex lock. When a process exits its critical section, it calls mutex unlock. If another process was blocked because the mutex was locked, that process is unblocked. Due to the simplicity, mutexes can be implemented in user space, provided that we have the TSL or exchange instruction. So this code is much like the code from figure 2.25, except we don't have that busy wait anymore. We don't have that infinite loop again anymore. Additionally, user threads have no clock to signal when other threads should run. If a thread tries to acquire a lock, it will loop forever and never acquire the lock, since no other threads are allowed to run. With mutexes, instead of a busy wait, a thread that's unable to acquire the lock, instead it calls thread yield. This gives the CPU to another thread so that thread can run in the meantime. Also, neither mutex lock nor mutex unlock require any kernel calls. This makes it very fast and very easy for threads to synchronize. The only caveat to this is threads have no problem accessing the same mutex since they have access to the same address space. How do processes share a mutex if their address spaces are disjoint? Processes have their own memory spaces. If two processes are trying to enforce mutual exclusion with a mutex, how can they? The semaphore could be stored in the kernel call. The semaphore could be stored in the kernel, meaning we can only access it using system calls. Alternatively, most operating systems allow processes to share address spaces with one another. This includes shared buffers and other shared data structures. So we can share memory between... We can share things between processes after all. And if all else fails, we can just use a shared file instead. There's another thing about what's called a mutex. If we have a spin lock, but the wait is short, then a mutex becomes fast. If there is much contention, it's more efficient to block the process and let the kernel unblock it when the lock is free. However, if there's little contention, switching to and from the kernel becomes an expensive operation. So the idea behind that is called, an interesting solution is called a mutex. Basically, a mutex implements a mutex, but without calling the kernel unless it has to. So in pthreads, there are system calls for creating and destroying a mutex. We create a mutex by calling pthread mutex init, and once we're done with it, we call pthread mutex destroy. The two functions that accompany a mutex are pthread mutex lock and pthread mutex unlock. If a thread had already... Okay, we're talking about threads now, so we're talking about using mutexes to enforce mutual exclusion at the level of threads. So this is pthreads, the multi-threading library. When a thread wants to acquire the lock, we have it called pthread mutex lock. If the mutex is already locked, then the thread that called it will be blocked. An alternative to that is this: pthread mutex try lock, which returns an error code instead. This allows the thread to do a busy waiting if needed. So that is a non-blocking call. Finally, when a thread has exited its critical section, we call pthread mutex unlock and release the lock. This signals to any waiting threads that the lock is now available for them to use. Pthreads also have another synchronization mechanism called a condition variable. Whereas mutexes are good for allowing and blocking access to a critical section, condition variables allow threads to block if some condition is not met. So pthread cond init and pthread cond destroy are used for creating and destroying a condition variable. Pthread cond wait and pthread cond signal are used to wait and signal. Wait blocks the calling thread until another thread calls signal. a thread called signal signals to other threads that they can now complete their wait operation. And both of these are atomic operations. The blocking thread is often waiting for the signaling thread to do some work, release a resource, or perform some activity. Only then can the blocking thread continue. Also, if there are multiple block threads, then we can use pthread-cond broadcast instead. We're just going to work with pthread-cond init, pthread-cond destroy, pthread-cond wait, and pthread-cond signal, alongside pthread mutex init, pthread mutex destroy, pthread mutex lock, and pthread mutex unlock. That's going to be part of our next assignment, which is trying out the producer's consumers problem. Okay? It should be noted that condition variables, unlike semaphores, have no memory. If a signal is sent to a condition variable on which no thread is waiting, the signal is lost. Care should be taken to not lose those signals. Looks like semaphores and mutexes make interprocess communication easy, right? Well, there's still an issue, and it is the fact that we have to call up and down in a specific order. If we forget to call up after we've called down, okay, forgetting the order in which to call up and down, forgetting to call one of them, or calling the wrong number of them, will break the mutual exclusion rules that we've been trying. And if we screw this up, we get something called deadlock, where processes are indefinitely blocked and no work gets done. So the following people here, Brinch, Hansen, and Hoare, H-O-A-R-E, they proposed a high-level synchronization primitive that they call a monitor. It's a collection of procedures, variables, and data structures grouped together into a package or module. Processes can call a monitor's procedures, but they cannot access anything inside. They cannot access any data structures inside. A monitor has one important property for enforcing mutual exclusion. Only one process at a time can be active inside a monitor at any time. A monitor is a programming language construct, so the compiler knows they are special and can handle calls to monitor procedures differently from other procedure calls. When a process calls a monitor, the first few instructions of the procedure checks whether another process is currently active within the monitor. If so, the process is suspended until the other process leaves, and if not, the process enters the monitor. With a monitor, it's the compiler that's arranging for mutual exclusion. This reduces the chances of something going wrong. The programmer who writes the monitor doesn't even have to be aware of the monitor arranging for mutual exclusion. All the programmer needs to know is turning the critical sections into monitor procedures is what enforces mutual exclusion. We're not going to be writing a monitor, but I would still like for us to try the mutex and the condition variables. We're going to write a multi-threaded pthreads program. We still, however, need a way to block processes when they cannot proceed. We do this by using condition variables and two operations called wait and signal. When a monitor procedure finds it can't continue, it does a wait on some condition of variable. This causes the calling process to block. If a process was previously prohibited from entering a monitor, it can enter now. This process can perform a signal on the condition variable the previous process was waiting on. There are a few caveats to this. Hoare proposed letting the newly awakened processes run, suspending the other one. Hansen proposed a process doing a signal must exit the process immediately. This means the last thing a process can do in a monitor is signal. We're going to use this implementation. This discussion uses this implementation. If multiple processes are waiting on a condition variable, only one of these processes is awakened. So we're going to tease through this in a bit. Okay, so a monitor is a construct that you would write using a high-level programming language, and this is a solution to the producer's consumers program using a monitor. We have wait and signal in here, like that of sleep and wake up, but there's a key difference. With sleep and wake up, one process may try to go to sleep while another process may try to wake it. In a monitor, this does not happen. So in Java, there is the synchronized keyword, which can be added to a method declaration. Oh, by the way, in Java, they're not called functions, they're called methods. Much like in C++, they're not called functions in C++. Oh, my bad. In Java, it's called methods, not functions, and in C#, it's called methods, not functions. When a thread calls a method... Okay, so this is the same code from before. This is the same pseudocode from the last slide, but it is all in Java. So, it might be a bit hard to notice, but yeah, so maybe I can full screen it for a better view. So Java has a synchronized keyword that you can add to the declaration of a method. When a thread calls this method, no other thread will be allowed to call any other synchronized method. Also, Java doesn't have any condition variables, so wait and notify operate like sleep and wake up, but it's not subject to race conditions. So this whole thing of code is a monitor written using Java. It uses the synchronized keyword so that only one process can, well, not process, but rather thread. Only one thread can call a synchronized method at a time. Once a thread calls a synchronized method, no other thread will be allowed to call another synchronized method. That enforces mutual exclusion. So the thing is, after all that, monitors still have issues. So a monitor, as I said, it's a programming language construct. The compiler must recognize a monitor and arrange for mutual exclusion. Languages such as C and Pascal, they don't support monitors. So if you want a monitor, if you want to write a monitor, you need a language that supports a monitor. Also, these kinds of languages do not support semaphores. But if you assume a semaphore-based OS, assuming a semaphore-based OS, these routines can be added as assembly code to the relevant files, which then issues the up and down system calls. Finally, both monitors and semaphores, they were made with one or more CPUs that can access a common memory. This doesn't work. This will not work for a distributed system because each CPU will have its own private memory. So everything we have talked about so far are everything that we have talked about so far are means of enforcing mutual exclusion to processes that are on the same system. If we have processes on two different systems, but the computers that they are on can communicate over each other on a network, we need a different means of sending information between the two processes, and that is message passing. So, with message passing, you are sending messages between processes that are on different computers. It can also work between processes on the same computer, but it is a bit slower because you have the overhead of creating a message and then unpacking the message. Okay, so message passing. In message passing, you have two primitives called send and receive. Like semaphores, and unlike monitors, these are system calls rather than language constructs, and you can turn them into library procedures. So, MPI stands for Message Passing Interface. That is a library you can use for C programs, and you can use that to send messages between processes that are on different computers. Or they could be on different computers. You can have a network of computers sending messages between one another using a message passing interface. So send sends a message to a given destination. Receive receives a message from a given source, or possibly any source. A process that calls this code can block until a message arrives, or it return immediately with an error code. So when it calls receive, it might be blocked until it receives a message, or it calls receive and gets an error code immediately because there wasn't a message to be received. So there are some design issues with message passing. These are unique to message passing. One, just like actual physical mail, you can get messages that get lost. You can have messages that get lost in transit. So to protect against this, the receiver can send an acknowledgement message back to the sender. If the sender doesn't get an acknowledgement message, the receiver sends a new one. However, the acknowledgement message can also get lost in transit. The sender must be able to distinguish between old and new acknowledgement messages. So send a message from you to someone else, and then they send a message back to you saying, "Hey, I got your message." But then the problem is that message that says, "Hey, I got your message," might also get lost. So that's one scenario. The other scenario is you send your message, but then your message gets lost in transit, and you, the sender, never get an acknowledgement message back. So you might want to try to resend that message you tried to send. Also, it's possible to send a message to an imposter. So to protect against that, you need authentication. This is a means of ensuring whoever is receiving the message is the real deal. Also, sometimes the sender and receiver might just be on the same machine. Message passing between two processes on the same machine is slower compared to other message passing methods, but there has been much work gone into making message passing efficient, even if it's between processes on the same computer. So once again, this is the Producers Consumers program using a message passing interface called MPI, which is short for Message Passing Interface. This is a well-known example of a message passing interface, and although I don't talk about MPI in all that great detail in the 4600, I do talk about it in CSE-5250. So in this setup, the producer produces an item. It receives, so it generates something to put in the buffer. It waits for an empty to arrive. Then it builds a message to be sent. And then it sends an item to a consumer. For the consumer, it receives a message with an item from the producer. It extracts the item from the message. It sends back an empty reply, and it finally does something with the item. So that's just a overview of what happens here. There is another means of synchronizing processes, and that is a barrier. This is a synchronization mechanism intended for groups of processes. Think of it like a traffic light. You have 4 processes that can all proceed at their own pace. To make sure they all proceed at the same time to the next step, you have a barrier that physically, I guess you can think of it, you can pretend that the barrier is a physical thing, and all these processes arrive at the barrier at different times. Kind of like a traffic light. Once every process has reached the barrier lifts, and all the processes are let through all at once. Some applications are divided into phases that require processes advancing to the next phase together. So that's what a barrier is for. An example of that can be found in, say, matrix operations. If you remember how matrix multiplication works, it might be one of the most the biggest headaches you may have gone through. But I like to think about matrix multiplication as just repeated dot products. If a dot product is basically repeated multiplication and addition, then a matrix product is basically a matrix where every entry is a dot product. So think about it like this. So if we have a matrix with values A1 through A9, and another matrix with values B1 through B9, the product matrix is also a 3x3 matrix where the entries are every possible combination of row vector dotted with, okay, so it's row vector of the first matrix dotted with the column vector of the second matrix. So it's every possible combination of row vector and column vector. So the first entry is row vector 1 and column vector 1. And the final entry is row vector 3 and column vector 3. So if we just pull out this dot product here, this is A1, which is little a, little a1, little a2, little a3, and then this b1 is little b1, little b4, little b7. So the dot product is a1 times b1 plus a2 times b4 plus a3 times b7. That entire calculation is this one value here. And then we repeat the same thing with all 8 other entries, but using different vectors for each one. So you could imagine synchronizing several processes so that they work on one dot product at a time. Although with this small an example, you probably would just assign one dot product to each. You might just want to assign one dot product to each process, but if we are dealing with, say, huge matrices, like on the order of thousands by thousands, then that's millions of calculations that have to be done. So we could, in that case, if this is, say, a 1000 by 1000 matrix product we're calculating, maybe we do want to synchronize it so that we have, say, 100 processes working on one dot product at a time. So yeah, that is an application for a barrier. For our next assignment, I would like you to try out the producers consumers problem. So we're going to try out writing a program using pthreads that uses a mutex and a condition variable. So that's going to be interesting to do and probably interesting to see once it's working, okay? So this is going to be posted a little bit later than I want it to, and that's because there's just so much material I have to prepare for this class. But anyway, that's going to be it for this discussion on synchronization, and once that's done, it's going to be your turn to try out synchronization methods, okay? Alright, thank you, and see you next video. Bye.